So today we're continuing this series of topical meetings organized by this CLARIPHY collaboration on AI machine learning topics and the intersection with physics. So Tailin Wu has agreed today to talk to us about accelerating simulation of PDEs in the context of physics. And on that note, I'll pass to Tailin.
Yeah, so today my topic is about learning to accelerate the simulation of PDEs. So this is a collaboration with Sophia, Jackie, Rex, Yuri, and also from Slack, the collaboration with Jason and Federico, and also with Palo Alps from UCLA. So simulations are very common in both science and engineering. For example, and also we can roughly categorize the simulations into 3 different categories. So firstly, we have the PDE simulations in which we want to simulate them on a fixed grid or a mesh. For example, there is weather prediction and also the aerodynamics and also oil production. Secondly, we have the simulation that involves both the field and the particles, and in which then we will have the simulation using the particle in cell method. This includes laser plasma particle acceleration, fusion, and also like the cosmic ray acceleration. And thirdly, the simulation contains particle-particle interactions, and it is usually use the graph-based method to do that. For example, we can have this water simulation and also some simulations in the astronomy. So among many of these simulations, although they are quite different in appearance, there are some common characteristics that are shared between them. So firstly, these simulations are usually very large in scale and at the forefront of the high performance computing. And even though they require so much compute, usually they can only simulate a small proportion of the systems. For example, for a reasonable 3D laser plasma interaction system, usually it will have like 100 billion grid vertices and 1 trillion particles, and we need to simulate them over 100,000 time steps. And even the largest simulation only can simulate 10% of that scale, and usually 1% of that scale. And secondly, these simulations usually are multi-scale and also involves a large dynamic range, which means that we cannot simulate this system using it on a large scale. We have to take into consideration the scales in smaller details. And also, in these systems, some of the dynamics in the microscopic scale can significantly influence the dynamics in the large scale. For example, let's take this system as an example, in which this laser accelerates this plasma. And in this system, there are only 0.01% of the particles are accelerated, but it can carry around 10 to 50% of the system's energy. And usually, to simulate these systems, to ensure the numerical consistency, we have to use the same granularity to partition this grid, so that we have to use the smallest scale in the system as the discretization, which means that for a majority of the system, although they don't need so much detailed scale, we have to simulate them with this detailed scale, which is a large waste of the compute, and which also points to a possibility of optimization, that we can accelerate this process using some better representation. So then the goal of our work is to really, for these large scale systems, to design a machine learning model that can learn an accurate and also generalizable model that can capture the essential dynamics of the system and also achieve speed up. And as we see before, that these systems usually have some characteristics that can endow some representation that can be that can describe its system with much smaller dimension. And therefore, our strategy is to use a latent evolution and learn such a latent evolution model for the system. Specifically, suppose that X is the input data, and then we can use an encoder Q to map it into a suitable latent space. And then we also have a corresponding decoder that can decode into the original space. We can also simultaneously learn an evolution encode operator that can evolve this latent vector in a latent space. And if the dimension of the latent vector Z is much smaller than X, then the K will be much smaller than if we have to learn the evolution between the original scale. And by this, then we can achieve speed up by evolving in latent space. And to do that, there are two questions we need to address. So firstly, how do we compress this input into a suitable latent representation? And secondly, how do we let the model to learn these dynamics faithfully? And to answer these two questions, it points to two aspects of the whole pipeline, which are the architecture and also the objective function. By architecture, I mean the specific design of the encoder or decoder. Like, for example, whether we use the graph neural networks or a convolutional network or a long-shorter memory. And for the objective function, I refer to like what is the main objective that we want to optimize, and what is the regularization that we can impose. And also, is there some auxiliary objective that we can also impose to encourage the model to learn the dynamics faithfully? And usually, the architecture is chosen based on the characteristics of the input. For example, if the input is a grid-based, then it is naturally to use a convolutional neural network. But if the input is particle-based, then it is naturally to use the graph neural networks. And the choice of the architecture also depends on some prior knowledge. And if we have some prior knowledge about some symmetries of the system, then we can also design the architecture to impose that symmetry so that it will learn better. And for the objective function, this will be the main part of my talk. And the design of the objective function will need to encourage the model to learn it faithfully. And the main difficulty is the following. As we see before, that in the end, we will need to evolve the system in latent space by applying the K multiple times, like hundreds or thousands of times. So any error, although very small, will accumulate, and possibly this accumulation is exponential. Therefore, it is very hard in general to learn this operator faithfully and evolve long time scale. And the design of the objective should encourage learning such good operator. So the objective we introduce is the following. It consists of 5 different terms. So recall that the Q is encoder, G is the decoder, and K is the evolution model. And the first component is a one-step prediction in which we apply this encoder to the input and then evolve it one time step and then decode and then compare it with the target at the next time step. And this is an MSE loss. The second component is the reconstruction loss, in which it just imposes that the encoding and then after decode, it can faithfully represent the original input. Thirdly, we also introduced this latent consistency loss. The intuition is the following. We can have the encoder that encodes to the Z of t, and then we evolve it I times. And then this evolved latent vector should be consistent with the encoding of the target in the future. And basically, this numerator will ensure that the evolved latent vector is consistent with the future target. And also, we have a denominator here, which is ensure that the network cannot cheat. Basically, if we only have the numerator, then the network has a freedom of a scalar in which it can just multiply this Q by a very small number, and then it can just achieve a very small loss. But it does not necessarily mean that it learns something. But once we divide it by this, like this norm, then it cannot cheat in this way. And if the
question,
okay,
when you say the norm, what do you mean explicit? Is it the sum in quadrature of all the elements?
Yes. So suppose that the Q is the Q of X is a vector. Then we just use the sum of the square of the different components. It is the 2 norm.
Thank you.
Mm-hmm. Yeah. And if the dimension of the latent vector is much smaller than the input dimension, then this loss is much more efficient than if we compute the loss in the original space. Because we can alternatively have a loss that it is like evolving it multiple time steps and then decode and then compare the target with the prediction. But then the decoded input may be much more high dimensional. But here, we can achieve the similar effect by constraining it in latent space. So fourthly, as we see here, that we can have some encoder, decoder, and some evolution operator. But actually here, there is a gauge freedom here. So suppose that we have an invertible function h that map some z to another different z in the same space. Then we can impose, for example, we can operate this h on the encoder and then operate the inverse of the h to the decoder. And then this new q prime, g prime, and k prime is still a valid operator that achieves the same result as the original one. So among many infinite tries of this q, g, and k, which one is better? So suppose that we have infinite data, like, then I think each one is the same. There is because they can represent the same thing. But because we have finite data to learn from, then there must be some one that are better because of the following. The model we learned by the K will definitely have some small error. It is not fully exact. And then any of the K error will accumulate multiple times. And then there can be some Ks that are very smooth, but there can be some different K that can be quite wiggled. And generally, it is much harder to learn some wiggled K than some smooth K, because it requires much more data to learn these very wiggled places. And therefore, our intuition is the following. Basically, we want the K to be simple and smooth so that it generalizes better. And quantitatively, we can constrain the Lipschitz constant of the evolution operator. Basically, the Lipschitz constant is the supremum of like how much an input change leads to a change in the target. And then if we constrain this K, Lipschitz constant, then any vary in the input will lead to a bounded variation in the output. And because our neural network K is generically a fit-for network, like the following, then we can have this upper bound of the Lipschitz constant by this following inequality. And basically, it is smaller than this product of the different Lipschitz constant of the different weights times the activation. And usually we use the radial activation or some leaky radial and so on, which has a bounded Lipschitz constant in this activation. Therefore, we can limit this Lipschitz constant by the Lipschitz constant of each of the weight. While the Lipschitz constant of the weight is actually the spectral norm of the matrix, which is the largest singular value of the matrix. And based on this, these three works basically introduce this kind of spectral norm regulation, which constrain the largest singular value of the weight matrix on each layer. And by this, it can indirectly constrain the Lipschitz constant and make it not wiggle so much. And in these three works, they also show that regularizing this spectral norm can improve generalization in deep networks and GANs. So yeah, this is the 4 components of the loss function. And for the 5th one, I will introduce later. So after introducing this objective, now we want to apply it to the different systems and test whether our objective and framework can learn these dynamics faithfully and achieve some speed up. And the system we investigate are the following. So firstly, we will investigate under this Navier-Stokes equation because it is a genetic benchmark that it is evaluated by different works. And also, it is relatively simple. Secondly, we will ramp up the difficulty and evaluate it in this plasma two-stream loss-of equation.
I'm sorry, can you just walk us through these illustrations a little bit? So can you explain, for example, for the Navier-Stokes equation, what's, in the lower left-hand corner,
yeah.
Can you tell us, what is on the horizontal axis? What is on the vertical axis?
Okay.
What the intensity means? Is one calculated using a traditional method and one from your method? What's the message?
Yeah, so actually here, I just show the figure. I will introduce that later in this next slide. Is that good? Yeah.
Thank you.
So, yeah, so basically, basically we will do it in these 3 systems. And firstly, we will do it on this Navier-Stokes equation. And for this Navier-Stokes equation, it is an incompressible Navier-Stokes equation in 2D, where we have 2 components in the velocity, ux and uy. And then basically, there is a cylinder here. And then the flow is flowing from this downward. And then what we show here is the ux component. And then the more green it is, the higher the value, where the white is 0 and red is negative. And then here it is like step 10 and 0, 10, and 20, and so on for the ux component. And here it is the uy component, which is the...
How are these calculated? Is this being calculated by a machine learned algorithm, or is this being calculated using a mesh?
Here it is simulated by a numerical solver developed by Neil's group. Basically, it is a ground truth solver that uses this Lagrangian method to evolve this equation.
So effectively, this is what you're going to call the equivalent of the ground truth as a function of time.
Yes.
And this is what you want to learn somehow.
Yes.
With your latent space and your evolution of the latent components, right?
Right. I want
Okay.
to learn from this.
Great. Thank you.
Yeah, thank you. And basically, we can see that here the diameter of this cylinder is 25, and the speed of this ux is 1 at this upper side. Therefore, we can calculate the dynamic timescale of the system to be this diameter over this u, which is 25 time steps. Which means that after 25 time steps, this system has evolved significantly. So we want to learn from this system, and we use the following architecture as the encoder, decoder, and evolution operator. For the encoder, we basically use a convolutional neural network with multiple layers. And then after 3 layers of convnet, we flatten into a vector and then apply 2 layers of feed-forward dense network to compress that into a dimension of 16. The original dimension is 256 times 128. And then the evolution model is of, let me see, a 3-layer feed-forward network that each layer maps 16 dimension to 16 dimension with, yeah. And then the decoder is symmetric with respect to the encoder that will decode back into the original time space. So before I show the success case, I will show some failed case in early times. And here, the upper one is the ground truth, and each is like 10 steps apart. And lower one is the prediction. As we see that even if we evolve time step, it is really quite good. After a few more time steps, then this error will accumulate. And then at last, it cannot be seen. It is too bad. And here it is the MSE versus the raw time steps. And the left-hand side is on the linear scale of MSE. The right-hand side is in the log scale. As we can see here, that the growth of the error is exponential with the raw time steps for this specific model. Let's look at the other one, another one, in which we see that 10 steps is quite good, but then after few more 10 steps, it becomes much worse. And then we can see that it is still grows exponentially. And usually it is very hard to learn this operator and evolve in long time scales. And now here we apply our full objective. And then here it is ground truth versus model rollout. And then here each is 50 time step apart. And then here it's 150. And then we can evolve like up to 400 time steps with almost exact like ground truth. And then here is the difference between the ground truth and our model prediction. Note that here, our model has some prediction here because in our training, we use some masks that do not compute the loss within the cylinder. Yeah. And then, so this does not matter here inside. But we can see that even after 400 time steps, most of the part it can represent faithfully. And here it is the MSE versus the time steps. And we can see that it does not show this exponential growth and mostly remain at around 10 to minus 2. And it can evolve around 18 different dynamic time scales. Also here, I plot the autocorrelation between the different x direction. So basically, I take 2 points within some distance in x, and then I compute the autocorrelation. between those points across different training, across all the different testing data. Oh, one more thing. So basically here, we perform our evaluation using a different test set with a different Reynolds number. So basically, we train it on 5 different new here, which correspond to a specific Reynolds number. But then for the testing, we are testing on a different Reynolds number. So we are really testing the generalizability of our model to like different scenarios.
So when you say different numbers, just to make sure, I assume that you're somehow training over, say, some range, a minimum range to a maximum range, and then you're testing the test samples inside that range and not outside. You're trying to interpolate rather than extrapolate.
Right. Yeah. So basically, suppose we are doing something like training at 100, 200, 300, 500, and then we test it on 150, 250, something like this.
Great. That makes perfect sense.
Mm-hmm. Yeah. Yeah. So here we can see that this autocorrelation also corresponds well to the ground truth. So now we will want to see how different components of the loss contribute to the.
Can I ask one more question, just because I was confused a few slides ago. Have you explicitly built into your network that the divergence of whatever is U is equal to 0, or is that just implicit in the mathematics of the generation?
That's a good question. So in this current model, we do not explicitly enforce that. This is encouraged by letting the model learn from the ground truth, because ground truth.
But it's not something that you've not added that as a boundary condition in any way.
So yeah, do you mean
you don't have a term in the cost function that enforces that?
We don't.
Okay.
But actually, we can choose to do it. So basically, in one of Neil's work, they designed the network architecture of the decoder such that it always output a curve of a potential. Therefore, the divergence of that curve is 0. We can also do this, but here I just want to see if we can, without enforcing this, we can learn something like this. Mm-hmm.
So could you also, so another metric in addition to your autocorrelations and your differences would be to explicitly calculate the divergence of U and take an average value of the divergence of U across the grid.
Okay, that's a very good
question. Another metric to understand how it's not your cost function; it's another metric of how good how well you're emulating the physics.
Yeah, that's a very good suggestion. We'll do that. Mm-hmm. Thank you. Any more questions up to now? Okay. So here we also see want to see like different components. How do they change? So here we test that without the latent evolution objective, what does it happen? And we see that basically it blurs out after just like a few tens of steps. And then here is the difference. And then we see that the error goes up like much larger than the previous ones. So thirdly, we also want to see that, like I said before, the consistency loss, if without the normalization, does it learn something useful? And here we see that without this normalization, that it does not learn as good as the previous full objective. because now the network has a way to cheat, but just by making this encoder multiplying a very small coefficient.
So just, this is new to me, so I'm slow, but this is putting the square of Q into the denominator. Is that right?
Right. Yes.
Okay. Thank you.
Mm-hmm. And then we see that the error goes up like later times. So fourthly, basically we have two ways to ensure that the latent space representation can decode into original space. One is using the reconstruction loss, and the other is using this one-step loss that compare the MSE on the input space. So firstly, we test without this reconstruction loss. And what does it shows? So we see here that it is still quite good, but at later times, it becomes blur a little without this reconstruction loss. So, and here's the difference. And here it is the MSE. We see that it remains good. And then at some point later, it goes up. So on the other hand, if we turn off this one-step loss, but remains the reconstruction loss, and let's see the performance. So we see that here it is quite faithful. And then the difference, we see that there's almost no difference around other part. And also here is the MSE. And interestingly, we see that this loss also remains quite constant across different time steps. Therefore, from this evaluation, we see that basically it seems that the reconstruction loss has a better effect than the one-step loss to ensure this learning faithful thing. And actually, we might only need this reconstruction loss. We might not need the one-step loss in order to learn this model well. So during the time, we also learn many other knowledge. For example, like we also try one case in which we predict, each time we predict the difference in target instead of the target itself. Basically, I mean that in the one-step prediction, instead of predicting the actual target, we predict the change in the target compared to the last time step. And what we find is that doing this may have a smaller loss in the short term, but it may diverge faster in the long term. Possibly because that when we predict the difference in the input, then we have to add this difference together over multiple times. And this addition may be biased up or down, and then this bias may accumulate. But if we only require that it predict itself, then it may not have this problem. Secondly, it is also common in machine learning to have this annealing of learning rate, that anneal down this learning rate during training. And we find that using the cosine annealing is much better than using this reducing learning rate over a plateau. And thirdly, we find that generally when we trained it, we use the one-step reduction loss to do some early stopping and to see the performance during training time. But this may not necessarily correlate well to the rollout performance in the long term. As we see before, that even if some rollout is very good in short term, it may have very large error in the long term. So this one step is not a good indicator. However, we find that a very small one-step loss is a good sign. Like, for example, if the one-step validation is already large, then it definitely is bad. If it is good, then it may be good in the long term. Just now I introduced that different objective components is plays the role. And as physicists, we also want our model to capture some physical conservation or constraint of the system. And there are two ways to ensure that. So we can design this constraint or conservation laws into the architecture. For example, as I said before, we can use this curl to ensure that the divergence is zero. We can also use this Hamiltonian network to ensure that the energy is conserved. The other way to encourage that is to build that known conservation laws into the objective. For example, if we know that the system is conserves energy, then we can add a regulation of that term into the objective. But here, because we evolve our model in the latent space, there will also have some new challenges. Definitely, we can, during training, we can also decode at each time step and then also enforce or encourage some conservation laws. But what if we don't know the conservation laws, which one it is? And how do we still encourage that and also encourage that in the latent space? So suppose that there exists some unknown conserved quantity like C of X that is conserved at different time steps. And then in our framework, this will correspond to some decoder operated on the V, and then it's conserved over different time steps. And the way we do this is through a GAN-like objective. Basically, we can train a discriminator which tries to predict that if the tool state conserves some quantity. For example, here we give the discriminator some ground truth, which we know that it must conserve some quantity. And then at the same time, we also give it some negative pairs, where the negative pairs is provided by the latent vector and also some evolved latent vector. Because during training, we know that this model is not perfect. Therefore, this quantity may not be fully obeyed. And then the discriminator is encouraged to find these not conserved ones, and then to try to learn such a model that can discriminate whether some quantity is conserved, and use that to make a classification of 0 or 1. And then we can use this Siamese architecture where the discriminator is obtained by using the same encoder on the two state, V1 and V2. Therefore, it will possibly encode some conserved quantity and then use this difference as a signal to determine whether it is conserved. And in this work, the authors basically use this Siamese architecture and with some different trajectories to train this network. And they are able to use that to discover some conserved quantity like energy or the angular momentum. But in here, we may not have such different labels. And specifically, then we just use the like the evolution of itself as the self-supervised signal. And this is the training. And during the inference time, we can use the discriminator to determine whether some quantity is conserved during the rollout. And then it can also provide some gradient if it is not conserved, and then correct for that. This is our proposed objective. And right now we are implementing it and testing it out. So up to now, is there any question? Okay, so going back to our our goal. So basically, just now we test our pipeline in this non-Westover equation, which is a standard benchmark and which is relatively simple in the sense that you can see that this system is periodic in that basically these these waves just wiggles around periodically. But what we really trying to do is to go into these much larger scale systems and then speed up these systems. So now I will introduce our like ongoing work or some plans on our plan on how to tackle this. So the next thing we want to tackle is this plasma two-string velocity equation, where this equation dictates the dynamics of the electron density together with the E field. And the B field is uniform in the background. And then here, the density is both in the X and also on the momentum space. And then here it is the ground truth data, in which this Y is the U direction, and then the X is here. And then this curve is the E field. And then the dark or lower color is this electron density. And this is a much more difficult task than the previous ones, because we can see here that as the time goes by, there are more fine-grained structures that are appearing. For example, as time goes by, these things become more narrow and more complicated like this. And also we see that this system is a kinetic equation, actually, because it is simulated by using the particle in cell method. And then what we show here is the density of that underlying particles. And after this, we will tackle this even larger system of the laser plasma system acceleration, in which there is a very fast, ultra-fast laser that is bombarding this material that make this material into plasma in an instant. And then the E field and will propel the the electrons and ions both backward and forward. And then it will bombard the material on the back, which can be used for different applications. And for a simple demonstration, we can visualize this in 1D case, in which here it is the X direction, and then here is the density of the plasma. And laser is shooting from the leftward. And here we also show the phase space density of the electrons, in which we see that as time goes by, originally the electrons have a velocity of 0, but then some electrons will be speed up into positive velocity, and then some will become negative velocity. And also this is the ion, and we see that the ion is much different than the electron, in which some ions are accelerated positively, and then some ions are accelerated negatively here. And then in the end, like this. And usually this kind of system is simulated in, with a particle in cell method. Basically, we can simulate the field using this grid, and then we can treat the electrons and ions as particles that is interacting with this field. And then the simulation method is usually like this, where we update the field based on the deposition of the charge density and current density on the field, and also the nearby field. And also then we can update the state of the particles by the nearby field. We don't do the particle-particle interaction because this will be O(n) square complexity. And we can simply use this field update to make sure that the update is local. So as we see before in this above two systems, the new challenges are the following, where this is no longer periodic. It is some transient dynamics. And then it is multi-scale. and has some fine-grained structure. And finally, the simulation is noisy and it is kinetic. So for the two-string Vlasov plasma equation, so we are doing the following encoding, in which we use the CNN plus the MLP to compress only on the U direction. Basically, we compress the velocity distribution, and then we can evolve this in the latent space with CNN, and then decode back into the original U distribution. And for example, originally U has dimension of 256, and we can use and compress that down to a 32 dimension. And here it is a ground truth and versus a reconstruction in which we use the above architecture. And right now we are doing this training to see how the evolution goes. I will hopefully have some results later. And by the way, so this kind of compressing the distribution has a close connection with the moment closure problem. Basically, we can describe this distribution in the U direction using moments. Like for example, the zeroth moments will be the density of the electrons at different x, and then the first moment will be the charge current, and so on. And then when we compress that to describe the dynamic equation, we will have to use a higher moment to describe the lower moments dynamics. Then there's a question of how to close this moment. And in this work, the authors use a neural network to ensure that the last moment is closed by enforcing some specific format in the last moment dynamics. And in here, we are also planning to do something similar, in which we can specifically use encode some first and second moment, like the rho and the j, and then we learn some generalized moment, and then also enforce that it is closed and it can evolve self-consistently. And for the larger system, where the ground truth is using this particle in cell method, we are right now using this graph neural network, and then to perform the encoding, evolution, and decoding, because it is much more suitable to do it in this graph-based, specific to this system. So yeah, so here right now we are implementing this, and hopefully there will be some good news in a few months. And so overall, in this talk, we introduced this architecture that try to evolve this dynamics in latent space so that it can achieve speed up. And also, we introduced this 5-turn objective to ensure that it can learn the dynamics faithfully. And also, for the architecture, we can design specific ones that are specific for the different problems. And right now we have this pipeline in which we can switch different objectives and architecture independently for different systems, so that we can just try different like objective or architecture with ease. Yeah, thank you very much for your listening. Any questions?
That's a very nice talk, Tailin. Questions for anyone?
Yeah, so I should let other people ask questions first. Then I've got a bunch. So this is a really impressive talk and really interesting work. And I don't claim to understand much in the way of partial differential equations. I know even less about partial differential equations than I know about machine learning. But one of the interesting questions, so if you go back and you show us some of the laser stuff, there.
You mean
Going back, there's one where you've got the ion going up and you still got something else going down.
Oh yeah, let me see. It's
And
like
that just makes me think about the fact that in many classical systems, the one you're showing just before this, that there is a possibility of chaotic behavior. That a very small change to the input at t equals to 0 can lead to very chaotic behavior after not so long a period of time. And what I don't know is what does your model provide for that sort of a possibility? That is, can you study chaotic behavior, or can you only simulate more or less well-behaved solutions?
Yeah, that's a very good question. So by chaotic, there can be on two scales. So suppose that we are simulating this particle system, and if we track the trajectory of each individual particle, then it is definitely chaotic in the sense that after many time steps, some change initially will result in like large change in the position of a specific particle. But for this system, a specific system, the distribution is not chaotic in the sense that we can still generally describe this system, this distribution in like more predictable way. And it is, we are also want to capture this by basically going beyond the individual particles and try to learn this collective behavior that is not chaotic on the individual particle level. But actually, for the previous system like this is an instability of the plasma in which actually I cut off the first part, in which at the first, this will be just some two straight lines. And then there are some instability happening that will cause this to be unstable. And then depending on where this instability happens, the later dynamics will be quite different. So currently, what I think is the following. I cannot answer for sure that if our model is able to capture this chaotic behavior like faithfully. But for these chaotic systems, if it is chaotic, then it is not to no avail that we can learn this for a long time step, like well beyond this chaotic region. But we can still make sure that the model evolve the system in a good solution space that can still obey like conservation laws and so on, so that it is still a physical system. I think for this, we will try to achieve. And this is a reasonable objective.
Okay, very interesting. What tools do you use to make these studies? What machine learning framework do you use? Something like TensorFlow or PyTorch, or do you have something that you built
PyTorch.
yourself?
PyTorch. We use the PyTorch library, and also for the graphing network, we use the PyTorch geometric, which is popular. Yeah.
And how long does it take to train a model? I mean, is it day, week, month?
Depending on the system, generally for the for this, let me see, Navier Stokes equation and also this Vlasov, it takes 1 day to train 100 epochs and to converge.
And that's on a single GPU or something like that?
Yes, a single GPU, yes.
And how long does it take to do the underlying calculations using grid methods, the numerical methods?
So let me see. So if it is like inference time, it is
not inference time. I'm just saying I'm not comparing inference time with the numerical methods. I'm just wondering how much effort has to go into producing the training samples.
I see. So in here, in all, like in the Navier-Stokes equation, we use some like open source solver, which like generally takes like 1 hour to generate those like, so like, let me see this data set. Basically, we have to generate like 10 different simulations. Each simulation is like 1,500 time steps. Yeah, and then we have to process the data, and so on.
But the order of days of processing time to create the training sets?
I think 1 hour for the Navier-Stokes equation.
For all the training sets?
Yes.
Okay, so not so much.
Not so much.
So this is something ordinary human beings can perhaps replicate.
Yes,
but you don't have to go to Oak Ridge and use a supercomputer to do that.
Actually, for these later systems, like laser plasma systems, we have to use this large cluster to generate the data set. Like for these ones, for the 1D case, in which we generally have like 10,000 particles and 10,000 grid. I'm not quite sure, but it may take 1 day and to generate this data set, where the size of the data is like hundreds of gigabytes.
Okay. Thank you. Like I said, this is a really interesting talk, a lot of really interesting ideas here.
If I may just add, just to complement here one of the answers about the details of some of these simulations. So we're collaborating with Tailin on the plasma physics side. So we're applying these techniques to plasma physics problems, and so we do many of these simulations, and some of the largest simulations we do of these laser plasma interactions can be on the order of millions of core hours. Okay, so this is the scale. So to produce one of these data sets, they would cost on the order of millions of core hours. Okay, a single simulation, for instance, a single.
Okay, so once this is trained, if you can actually replicate this with an inference engine that runs on the order of a day, that would already be very useful.
Precisely. So exactly. That is exactly where we want to go. Okay. Actually, when I say 1 million core hours, we can actually do this in less than a day if we use the world's largest machines. Okay, but you really need a few hundreds of thousands of cores to run it in less than a day, right? But we want to bring that computational cost down, and we believe we'll be able to do that for many of these problems, and that's what we're aiming for.
Great.
Let me just add one more thing. Regarding the computational gain in running these things with so comparing the machine learned evolution with the original solvers, grid-based solvers, the traditional solvers for evolving these systems at these small scales, these small tests. I don't think we will see a big difference in gain. The place where we will see a transformative gain, okay, orders of magnitude speed up, the place where we expect to see these large speed ups is when we go to 3-dimensional systems, really large scale simulations. There we expect to get significant speed ups. yeah, so that was the last addition I wanted to make there.
Okay. And so the particular application you're looking at when you talk about plasmas, what sort of plasmas is a particular application? Is this the plasma accelerator work being done in Slack or something like that, or?
Yes. This project started because we're trying to. There's going to be a significant upgrade on one of the laser systems at Slack, which will allow to do laser-driven ion acceleration. And in order to optimize this source of ions, we need 3D modeling of these systems. The 3D modeling is extremely expensive, these systems, and this is what has motivated this line of work. So it is
Fantastic.
I
love the application as well as the machine learning part of this.
Great.
Thank you.
Thank you.
Okay, we're almost at, we're at 1 hour. Any other last questions? Okay, so well, Tailin, thank you. This was really interesting. And more soon. Thanks, everybody.